Welcome to the video on powers of complex numbers. In the previous video and in your classwork, you should have learned that when you start raising a complex number to a power, the work can get pretty overwhelming. So, for example, we started with z equals 1 plus root 3i, so a number in its a plus bi form. If you wanted to raise it to, let's say, the third power, I would have to take that number and actually multiply it by itself 3 times. Right? I would write it out like this. And I can only multiply 2 numbers at a time, so let me start with the first two. That would turn into 1 plus 2 root 3i plus 3i squared. Right? And I'd still be multiplying that by 1 plus root 3i. Can you imagine what this would be like if I had to do 8 of them? Right? So in the classwork, you actually learned a shortcut, which I'm going to do in a second. I'm just going to finish this first. I squared, that's really -1. So let's change that to a -3, and we can simplify this a little bit. We get -2 plus 2 root 3i. And let's do the final multiplication here. We're going to get -2 plus 2 root 3i minus 2 root 3i plus 6i squared. Okay, so that's going to become -6. So we add up our real terms, we get -8, and it looks like our imaginary terms are going to add up to 0. Okay, so we're done. So z cubed in this case would be -8. But in your classwork, you realize that if you changed this from a plus bi form into trig form, and this number in trig form happens to be 2 times the quantity of cosine pi over 3 plus I sine pi over 3. If you need help finding where that came from, just watch the video previous to this one, how to go from a plus bi form into trig form. So now that I'm in trig form, we learned at the end of the classwork that really all you have to do is take that power, raise the radius of that power, and take the angle and multiply the angle by that power. Right, for both the sine and the cosine's angle. Like that. So let's simplify. We get 8 for the radius times cosine of pi plus I sine of pi. And then I know what cosine of pi is. That's -1. I know that sine of pi is 0. So we get -8. Well, it's a good thing. We better get the same answer. We're doing the same problem. Even when we're cubing and the work in a plus bi form isn't super overwhelming, I still prefer this new method. So we're going to give this new method a name, and it's called Moivre's theorem. So it says if you have a number in trig form, as so, and you want to raise that number to any power, let's call that power n. Take the radius, raise it to the same power, and take the angles and multiply it by that power. It's a very nice theorem. And you really should have just discovered that on your own. It's pretty easy to see if you do a whole bunch of these problems out. So we have this Moivre's theorem. Let's see if we can use it to do some problems that we really wouldn't want to do something in a plus bi form, like the z to the 8th power. Right? I don't want to do that in a plus bi form. So how am I going to do this? Well, the first thing I'm going to do, I'm going to write this number in trig form. And throughout this video, I'm going to continue with the same complex number so we don't have to waste time converting. Right? If you need practice converting, again, watch that previous video, do some other problems from the textbook, Khan Academy. And now that I'm in trig form, we use Moivre's theorem. So z to the 8th power. Take that 2, raise it to the 8th power. Take your angle, multiply it by the power, which is 8. As so. And now let's do some simplifying. 2 to the 8th, that's going to be 256. My angle is going to be 8 pi over 3. And 8 pi over 3, that's bigger than 2 pi, right? Because 2 pi would be 6 pi over 3. This is 2 pi over 3 beyond one full circle. So I'm going to find that coterminal angle that I can work with of 2 pi over 3. And now I can actually know what this number is in a plus bi form, because the cosine of 2 pi over 3, if you want to draw a little picture here, 2 pi over 3 puts us in quadrant 2. The angle, or I should say the reference angle, is 60 degrees. This would be a root 3, this would be negative 1, this would be 2. So cosine would be negative 1/2. Sine would be root 3 over 2. So now if I distribute the 256, I get negative 128 plus 128 root 3i. So it takes the same amount of work no matter what this power is. Right? That's a very useful tool to have. But what happens if that power is a fraction? So we made this problem have a fractional exponent of 1/3. I hope you remember that that really means a cube root. Well, de Moivre's theorem still is going to work. So let's set that up. Again, I kept the complex number the same, so I'm just changing it into trig form. As so. I'm going to raise the number to that exponent, right? So we take the radius, raise it to that same exponent. We take the angle, and we multiply it by that exponent. Okay, so let's see what we get here. It depends on how you prefer to write this answer. 2 to the 1/3 power. It's the same thing as cube root 2. Some people prefer writing it as the cube root. I don't think one is better than the other necessarily. For our angle, that's going to simplify to pi over 9. And now we're in a situation where I don't know the cosine or sine of pi over 9. Let's leave our answer in trig form. Okay, so there's our answer. But if you remember, when you take roots, you get multiple answers. So where are the other answers, and how many are there? When you take a square root, you get 2 answers. When you take a cube root, you should get 3 answers, and a 4th root, 4 answers, and so on. So, where are they? I'll show you where they are. I'm going to draw a picture of my first answer. My first answer has a radius of the cube root of 2, has an angle of pi over 9. So as a polar coordinate, it's, I don't know, about here, right? So radius is cube root 2. I'm going to write the angle out here, pi over 9. It turns out that whenever you take roots, that the roots are all equally spaced along a circle with the same radius. So here's my circle with a radius of cube root of 2. If they are equally spaced, and there are 3 of them, think about how far apart they would be. A full circle is 2 pi. There are 3 of them. I'm going to divide that by 3. Well, there you go. That means cube roots are 2 pi over 3 apart. If I was doing 4th roots, they would be 2 pi over 4 apart, or in other words, pi over 2 apart. So that's pretty easy to figure out. So now we have one answer at pi over 9. The next answer is pi over 3 this way. Oh, sorry, 2 pi over 3 this way. About here. So let's see, pi over 9 plus 2 pi over 3. Let's add those together. Let me change my denominator here. I'll multiply by 3 over 3. That becomes 7 pi over 9. Perfect. That should be in quadrant 2, right where we put it. So my second answer, let's list it down over here, same radius, but a different angle. 7 pi over 9. And let's go another 2 pi over 3. I think that puts us in quadrant 3. Let's see if that makes sense. So 7 pi over 9 plus 6 pi over 9, right, that's the same thing as 2 pi over 3, gets me 13 pi over 9. That sounds right, because I think 3/4 of the way would be 13.5 pi over 9. So our third answer has the cube root of 2 radius, but an angle of 13 pi over 9. And if you really want to, I know I do it all the time, I check. I add another 2 pi over 3 and see if I get back to pi over 9. Now obviously you're not going to get exactly pi over 9, you're going to get 2 pi plus pi over 9. In this case that would be 19 pi over 9, which is exactly what we would get if we added 6 pi over 9 to 13 pi over 9. So I do a little check in my head to make sure that it comes back to where we started. So we have these three answers. Now before I move on to the next example, I just want to show to you, you've actually been doing this every time you take square roots. Think about it. The square root of 9, you've just been writing down plus or minus 3. Where is plus 3? Well, it's right over here. Where's minus 3? It's right over here. How far apart are they? They're pi apart. They're equally spaced out on a circle of radius 3. So you have been doing this every time you've been taking a square root. Okay? So now, let's do another one of these problems, but let's change the complex number. So for roots of unity, what does that mean? Usually unit in math means 1. Unity actually does mean 1. We are going to find the roots of 1. Well, there are different types of roots that we can find. This question, we're going to find the third roots, right? That's also known as the cube roots. So to begin, let's write the number 1 in trig form. What would the angle be if you're at 1? Here I am at 1. What's the angle? I'm at 0. So cos of 0 plus I sine of 0. Now I want to take the cube root. I'm going to raise to the 1/3 power. I'm going to take the angle. I'm going to multiply by that power. Okay. Cube root of 1. That's actually 1. Cosine of 0 plus I sine of 0. So the first root is actually itself, right? Because we get 1 times the cosine of 0, which is 1, plus 0i. 1. First answer. They're cube roots, though. So they are 2 pi over 3 apart. That means we are at 2 pi over 3 for our next answer. Let's write that down. Cube root of 1 times the cosine, 2 pi over 3, plus I sine 2 pi over 3. So let's go into a plus bi form. We get 1. Cosine of 2 pi over 3, we just said that that was -1. And, sorry, -1/2. And then we're going to get positive root 3 over 2 for the sine. So our second answer is -1/2 plus root 3 over 2i. And lastly, another 2 pi over 3 brings us to 4 pi over 3. So now I need to know what the cosine and sine of 4 pi over 3 are. That's going to be -1/2 and negative root 3 over 2. So we have our last root in a plus bi form right there. So remember, if you were doing the fourth roots of unity, you're still going to get 1. But they would be pi over 2 apart. Wouldn't they be 1, -1, I, and -i? Okay, so lots of stuff we learned in this video. You definitely need practice on this. First thing you're going to do is go to that textbook, get those problems done. If you feel like you need more, look at more problems in the textbook, especially the ones that have the answers. Go to Khan Academy. Remember to write down any questions you have and ask in class. We'll see you there.